Good morning, everyone, and thank you, KG, for the introduction. Pleasure to be here with you today. So, session is about creep and shrinkage of SCC, and looking forward for the session. You see here three logos because this is where I work at Missouri S&T. But when this work was done, it was in Canada at the University of Sherbrooke, and the student who did this work. It was a team, but the main person who did this work is Wujian Long, who is now a professor at Shenzhen University in China. This is a work I'm presenting was done under NCHRP 1812 for SCC for Prestressed Precast members. And what I'm going to cover today is just very briefly about background about creep and shrinkage and why we have to worry about this behavior for SCC. Talk about some of the mixtures that were tested under this program, some of the test methods to cover autogenous shrinkage, drying shrinkage, and creep and compression. These are pre-stress members, so creep is very important. And then we're going to look at some of the models that are used by AASHTO, but also other codes to evaluate shrinkage and creep and autogenous shrinkage, and see how they apply to these mixtures that are quite different, and if there's anything we can do to modify these models to enhance the prediction. And then I'm going to cover briefly some statistical models to show you what are the parameters in the mixture proportioning that are very important for shrinkage and creep, and then talk about the behavior, again, only shrinkage and creep for AASHTO type 2 girders. So when you look at these couple of bullet points, you see that when we are working with SCC, we are in trouble when it comes to shrinkage and creep, because SCC by design has higher paste content, has a lot of fines, ultra fines, less than 125 micron, to promote better workability in rheology. So all of these are going to tell us that, yes, your mixture, if you don't modify it, it's going to have more shrinkage, it's going to have more creep, and also it's going to have a lower elastic modulus. When we use superplasticizers, such as the polycarboxylate ethers that are targeted for precast, pre-stress applications, we want very high early strengths. And that also can bring on some issues with autogenous shrinkage at early age and later behavior. All right, so if you look at, in the NCHRP, we tested 32 mixtures, variety of binders, but then we started workability, mechanical properties, and when we got to viscoelastic properties, we knew that there are certain binder types that are not going to give us the strengths that we need. So we reduced that, and we ended up with 16 SCC mixtures. So here you have the SCC mixtures with binder contents between 440 and 500 kg per cubic meter. If you want to convert to pound per cubic yard, divide by 0.59. I should have put them in parentheses. The water to binder ratio, 0.34 to 0.4. You'll see that the strengths that we're looking for is about 50 to 70 MPa. A release strength of 35 MPa, which is 35 MPa, 6,000 psi. 5,500 psi, and he's saying yes. The mixtures had VMAs in some cases, or in other cases, no VMAs. The binder, we tried two binders. Again, we're concerned about the 18-hour breaks. So the binders were either moderate sulfate, which is a type 1-2 or type 2 cement, or high early strengths, which is type 3 cement plus 20% fly ash. Since this is NCHRP, we had to look at what took place across the country, and this was the country, US, although the work was done in Canada. So we also tested slag cements with type 3 cements. At the high performance, you see the water binder ratios were 0.34, 0.38, lower slump, 6-inch slump, and the same binder types. And for the aggregate, all the concretes were prepared with half-inch maximum size aggregate. All right, for shrinkage testing, we started with autogenous shrinkage. So the way we do this is we have our prisms, and we put inside them vibrating wire gauge that is embedded. It allows you to measure temperature and also the strain in the concrete as the concrete starts to shrink. You get the measurements immediately at the set, so you don't have to know when the setting time is. And then you do have to correct for the length changes of the concrete due to temperatures. So you have the temperature, we measure coefficient of thermal expansion, contraction, and we get the pure shrinkage. So after 1 day, we demold them, and then we wrap them with self-adhesive aluminum paper, 2 layers. We measure the mass, and there's no mass loss, and that's why we call it autogenous. So all the shrinkage is really internal. It's due to, George told me, give some background before my lecture, so I'm giving some background, George, you don't have to cover that. But it's mainly due to self-desiccation and also chemical shrinkage. And these are the results of 8 of the 16 mixtures. And you can see that there are 2 colors, really. The blue one would be the first one, the water cement ratios or water binder ratios of 0.34, and the lower ones, or the red ones, are 0.4. So you cannot say that one is better than the other, because there's other factors also, the other factors being the binder type. But you can see in general, the autogenous shrinkage drops very quickly, about 7 days, and then it's pretty stable. We measured it up to almost 75 days, but you see that the strain is between 100 and 350. That's not very high. For those of you who are working with UHPC, that can be 800 microstrain, same as a shrinkage of regular concrete. But high performance concrete has 100 microstrain. So again, the binder type affects very much autogenous shrinkage, water binder ratio, all the fines. There are not many models in the literature for prediction of autogenous shrinkage. So we found 3 models, and by the way, as a disclaimer, this work was published in 2009. So anything I'm presenting here is the knowledge up to that time. There are probably other models since then. But the very famous model for autogenous shrinkage is by Tazawa and his group at Hiroshima University in Japan. And you can see that the model, if you don't modify the model, you get a coefficient R squared of 0.34, just a cloud. And then what we did is we modified the model by inserting here what is in pink is eta, which is a coefficient to take to calibrate for the cement. A lot of the autogenous model shrinkage models take into account the cement, because that's one of the factors, along with the water to binder ratios, that have the highest effect on autogenous shrinkage. So you can see that the prediction is almost 1-to-1. They're scattered, but the R squared is a lot better. And then for drying shrinkage and creep, we tested the samples. For creep, we had to simulate what happens actually in a precasting plant. So we had the samples air dry in the molds actually for 16 hours. And then between 16 and 18 hours, we had to demold them, mill them on both sides, and apply the pre-stressing load. So these are very high strength creep cells, and the pre-stressing load corresponded to 40% of the compressive strength at 18 hours. So you can think about timing when you're going to cast the concrete, so the students are back in the lab 16 hours later, working very, very hard to mill and measure compressive strengths and load those 3 samples, 1, 2, 3, of the same mixture at 18 hours at 40%. And then they were in ambient temperature in the lab, humidity is controlled, and we tested that for 11 months. And you measure both the shrinkage and the creep of those samples to be able to deduct the various values. And we did the same thing for shrinkage, except we cast prismatic members, STM 157. We let them moist cure for 7 days and then air dry at 50% for about a year. For the steam curing, this is a steam curing regime that we followed. Sorry, I misspoke. After a couple of hours, we started steam curing the sample. So all the samples were steam cured. And then by 18 hours, they achieved a certain strength, and that's when we applied the pre-stressing. Yeah, steam cured for the creep. The targeted strengths at 56 days were 55 and 69. So 69 is 10,000 psi, and 7,500 psi. We're covering different places in the country, and I remember one of the panelists, actually Dr. Schindler was one of the panelists, but one of the panelists from Seattle, from Washington DOT, was very adamant about having very high strengths for those precast pre-stress members. So 10,000 psi was the minimum. All right, so again, we've done 16 of these, and you saw that these are averages. The water cement ratios, in this case, is 0.34, and when we have two binder contents. So the red ones are with the higher binder, and the green ones, the blue ones are with the lower binder content. And again, you cannot say that always a higher binder content, i.e. higher paste content, has more creep. It's not always the case. But the values varied between 500 and 1,000 microstrain after 11 months. Whereas the high-performance concrete, we tested two of those, were slightly lower. I wouldn't say a lot lower, but just slightly lower. So in general, having tested 16 of them, we can say that on the average, 30% higher creep can be expected for SCC versus high-performance concrete. So again, it's because of the higher content of paste, but I must say that we can always adjust for that. Knowing that your material is going to shrink and creep more, you can always reduce the water binder ratio. There's admixtures you can use, so you can design for that. Right. So this is the creep. The creep you see over here for the 0.4 water binder ratio. Also, the values range between 1,000 to 1,450, and they were 20% higher than those of high-performance concretes. And now, if you look at the models, we looked at all these models. Of course, we're interested in AASHTO because the whole project for NCHRP had an objective of modifying the AASHTO code, LRFD code. But you see the codes, some of them do take into consideration the cement type. Cement type, water binder ratio, compressive strengths. Of course, the age of loading is very important. Curing condition, steam versus water curing, and all of them take into consideration the volume of the element versus the surface area. This is a drying surface. So yesterday I was in the Shrinkage and Creep Committee, and that's a committee that really, where we have experts who worked very hard to try to develop models. So some of these models come from committees like ACI, AASHTO, CEB, and others. But these are some of the models, and I'm not going to go through the details. I'll just point out a few things. So you see all the coefficients, humidity factor, relative humidity, volume to surface area, time-dependent factor, maturity, compressive strength that is specified. These are the AASHTO models. And some of the other models also take into consideration the one that is the CEB-FIP that is underlined a beta factor. It takes into consideration the cement type. So cement type is very important. The same thing with the GL model, the GL 2000 models. We have one of those model developers sitting ahead of us, Professor Nassif. All right, so if we compare our 16 mixtures to the various models, and if you look at, for example, the AASHTO, the second one, the AASHTO 204 model, R square of 0.75, and by modifying the cement coefficient to account for the cement types that are specified for the SCC, you could see that the quality of the model is improved quite a bit. Again, so there's no science behind it. It's really fitting the data to give you better estimates based on a lot of data that is generated at various ages during that testing and for various mixtures. Okay. So the CEB-FIP 90 model without any modifications also gave a good prediction. It was an R square of 0.8. Otherwise, the AASHTO model was modified. The same thing for drying shrinkage. There's a lot of models out there for drying shrinkage. And the one on the top is the modified AASHTO. That gives us a very high R square. And the points are really, the points there that are the empty triangle, black triangle, which follow pretty much the linear one-to-one relationship. All right, and then we have the prediction. So in terms of prediction for drying shrinkage, again, we introduced this coefficient A that is a cement coefficient, and then you have two coefficients, 0.91 and 1.06. Those are the coefficients for the two types of cements that are proposed or that were tested. And then there's other models, and again, I'm not going to go through all of them. All of this work is published under NCHRP. It's free to download. And when you go to CREEP, you can see the blue points are the original AASHTO codes, 2007. And by modifying the codes, you can see that the modified code with the triangles, empty triangles, you get much better quality of prediction, although there's also at the lower end is very, very far from being precise, even with the modifications. So the coefficients for the cement factor A are listed over here for the modified AASHTO code. All right, so for autogenous shrinkage, we thought that the model from Tazawa and Miyazawa with some modification really captured very well the autogenous shrinkage of SCC, and the drying shrinkage, the modified AASHTO codes, and the original CEB-FIP code did a pretty good job. And the CREEP, again, the CEB did a good job, and the AASHTO had to be modified. Our main objective really in this study was to modify the AASHTO code. So this was 2009, this is AASHTO 2007. And then looking at what are the factors that really are important if you were to design an SCC mixture to develop low shrinkage and low creep, what are some of the factors and how does they stack? So for that, we did some experimental design using central composite approach where we modeled the behavior of the various parameters that I'm listing over here, 5 of them, between a lower value and an upper value. For example, for the binder content, we said for SCC for prestressed precast application, we're like between 440 and 500s, the water binder ratio between 0.34 and 0.4. So we model that, and we have a range over there that we see that the crisscross, we modeled that. So we used 16 mixtures, 4 central points, and then 8 what we call axial points, those are validation points. And then you can start doing some trade-offs. For example, these are contour diagrams of the autogenous shrinkage that are on the contour diagrams, where you have on the vertical axis the binder content, horizontal is the water binder ratio. And you can say, if I increase my water binder ratio for a given binder content, how much is autogenous shrinkage? So you can kind of see trade-offs, and then you have to have other parameters that are on top. We don't have a pointer. This pointer, it's okay. It doesn't work. It's all right. There is? Yeah, I'm trying to. Oh, it's hiding. Oh, thank you so much. So see over here the parameters that are fixed, the other model parameters. So in general, we see, for example, if we go from a type 2 cement to the right side, type 3 cement with 20% plus fly ash, you get about 20% higher autogenous shrinkage with everything else is constant. So the binder type really makes a big difference. And here another simulation for, again, the binder type, but here is drying shrinkage instead of autogenous shrinkage. And the contours are the 56-day or 112-day drying shrinkage. And again, you can see the trade-off. And the right side was a type 3 cement, fly ash is higher. So you could do this and then develop, and I'm not going to bore you with the details, but I encourage you to go and look at the report. There's a summary of the report that is pretty concise. But these are the models, statistical models. Everything that you see, water binder ratio, BT binder type, etc., they are encoded values, -1 to 0 to +1. So if you see something negative, for example, let's look at the drying shrinkage at 112 days. You see that there's a 554 microstrain as a measurement minus something. So when it's minus, that means by increasing the water to cementitious materials, there's a reduction of drying shrinkage. When it's plus, that means it's an increase. And they are listed in order of importance. So the first one is water binder ratio. You see it's very important. That means it's the factor that is the most important. And granted, if you change in materials, the response will change. But what's interesting is that knowing what the trend is. So if I were to take this and say, okay, I'm going to use the slag cement or I'm going to use different aggregate, I know what are the two most important parameters to go and do some testing and mixture development. So if you were to make some recommendations, and here the last three rows are the ones about viscoelastic properties, but you also have the 18-hour strengths, modulus, flexural strengths. The darkened areas are the areas where you will get better behavior. So if you were to look, for example, water cement ratio, water cementitious between 0.34, 0.40, you see, as you would expect for all the mechanical properties, the lower one is better. But if you look at autogenous shrinkage, the upper one is better. Drying and creep, the lower one is better. So that's the way to read that. So if we again concentrate on the drying shrinkage and creep, you can see that the areas that are highlighted are where you would expect better behavior. And finally, I'm just going to present not the structural performance, but what we measure in terms of shrinkage when we did some girders. So we cast some girders, type 2 girders, AASHTO, in the lab using ready-mix concrete that was delivered. And we specified target strengths at release of 35 and 43 MPa. They were steam cured. And then the design strengths again is 55 and 69 MPa. And these are the mixtures, so they were cast and tested in flexure and shear. But you have the slump flows and then 2 high-performance concrete and 2 SCC mixtures. Water binder ratios 0.32, 0.38, and was a different type of binders. And the performance pertaining to really shrinkage and creep. In terms of mechanical properties, the 2 SCC girders had very similar behavior as those for high performance, but including the autogenous shrinkage, we did measure 20% greater drying shrinkage than the comparable high performance concrete. When I say comparable, it's the same water binder ratio, same binder. The shrinkage, the high shrinkage also led to more camber. So that's one of the important aspects of shrinkage. And then SCC and high performance concrete with similar compressive strengths exhibited also similar transfer lengths when we release the pre-stressing and measure the transfer lengths inside the concrete. So if you'd like to learn more about this, there's a very nice synthesis that NCHRP requires, and you can download that. It's free online. It's report 628. Is that? Thank you.